Now we'll start talking about solving logarithmic equations, but first we want to do a reminder of finding the domain of a log function, just because that will definitely come into play when we're solving logarithmic equations. So down here for number 9, we're asked to state the domain of each log function. And over here on the left side, I just wrote a reminder, log base b of x equals y, if we're looking at that. The domain of the log portion, we can only take a logarithm of an argument of something that is positive. So in that case, x has to be greater than 0. X has to be positive. And over here in the calculator, if I take I'm using the common log button, so just that log, but I could do this with the ln key or with that log base key under the math menu. If I take log of 5, it's whatever it is. Log of 10 is 1. Log of negative 5 is not a number. It's an error message. Okay, you'll get some sort of error message on your calculator. And even log of 0, some sort of error message on your calculator. It might be a different error message, but your calculator is not going to be happy. Okay, so if we take the log any base of 0, calculator's unhappy. If we take log base b of some negative number, calculator's not happy. But if we take the log base b of a positive number, yay, our calculator cooperates. All right, so the moral of the story is whenever we're taking the logarithm of something, that argument needs to be positive. So when we're asked to find the domain, like in part A, f of x equals log base 2 of x plus 2, the argument, the thing we're taking the log of, has to be positive. And then we just solve that. Oops. So we get x greater than negative 2. And then if we want to write that in interval notation, that would be negative 2 to positive infinity. All right, part B, g of x equals natural log of x minus 5. The argument, the thing we're taking the log of, x minus 5, has to always be positive. So we set that greater than 0. And this means x is greater than 5. So interval notation, 5 to infinity. Okay. And for part B, since we've got the ln key on our calculator, I've got that ln key. So what this is saying is if we take that function, so natural log of something minus 5, if I take like natural log of 7 minus 5, if x equals 7, all good. If we take the natural log of 3 minus 5, not so good, right? So anything in that interval from 5 to positive infinity, anything greater than 5 to positive infinity is going to work. So if I take natural log of 5 minus 5, calculator doesn't work because that's the natural log of 0, right? So that's what this domain is telling us. It's which x's are allowed so that we don't make our calculator angry. All right, so we're going to use this fact as part of solving these logarithmic equations. And just like with our exponential equations, we've got kind of two basic techniques, two types of equations we're going to run into. And very informally, I'm writing this type 1 as a log equals a constant. So if we take a look at number 10, you see log base 3 of 3x minus 2 equals 2. So a log on the left and then a number on the right, a constant on the right. So we're going to follow these 4 steps up here in purple. First, if appropriate, you're going to condense logarithms. So you just want one log on one side of your equation. Step 2, rewrite in exponential form. Step 3, you'll solve that equation. And then step 4, you're going to check the solution that you got, or solutions, I should write solutions, and see if there are any domain issues. All right, so for number 10, log base 3 of 3x minus 2 equals 2. We can't condense that because it's already one single log. So now we'll rewrite in exponential form. So base 3 raised to the power 2, so there's 3 squared, 3 to the power 2, equals 3x minus 2. And then 3 squared, of course, is 9, equals 3x minus 2. And then we're just solving from there. We're adding 2 to both sides to get our 11 equals 3x. Divide both sides by 3. We get x equals 11 thirds. Super. Now our final step is we need to check. And when we're checking, what we're really checking is we just want to make sure that whatever the log is, whatever log base we have, we just want to make sure that we're taking the log of something positive. So if you want to fully check and make sure that the left side equals the right side, that's super, but the only required check is just make sure that you are taking the log of something positive, regardless of the base. So looking at our original function, we have log base 3 of 3 times x. Just going to put this in parentheses right now. 3 times x, switching colors, minus 2. And I don't even care about that right side. We can write equals 2 for now. But really what I'm focusing on is I want to make sure this argument is positive. So we're proposing the solution 11 thirds. So 3 times 11 thirds, cancel out the 3's top and bottom. So that gives me 11 minus 2, which of course would be log base 3 of 9. And these are nice pretty numbers, so I can't actually see that log base 3 of 9 equals 2, so the whole equation works. But really all I'm checking is that 9 is positive. The argument is positive. That's all that I need to check. Okay, so 11 thirds is a valid solution. Yay, we're done. When we go over to number 11, we don't need to isolate or condense the log for step 1. So we're going to go to step 2, rewrite in exponential form. So 5 squared, 5 to the power 2, equals x squared plus x plus 5. And of course 5 squared is equal to 25, so let me rewrite it as that. So 5 squared, there's 25. And I see that we have a quadratic equation here. So let's go ahead and set the equation equal to 0 by subtracting 25 from both sides. So I'm going to rewrite this equation as x squared plus x plus 5 minus 25. Oops, sorry, so that's going to be minus 20 equals 0. So I just subtracted 25 from both sides to 0 out that right side. Erase that. All right, so now I'm going to try factoring, and if factoring doesn't work, I've always got the quadratic formula I can use to solve this, but I think factoring is the easiest way to go here. So I can factor this and get x plus 5 times x minus 4 equals 0. Set each factor equal to 0. And I solve these and get x equals negative 5 or x equals positive 4. So those are my two proposed solutions. And they both could be fine, but let's go ahead and check both of these. Okay, and remember the thing that I'm focusing on is I need to make sure that this argument that I'm taking the log of is positive when I plug in these potential solutions. All right, so let's check x equals negative 5 first. So for x equals negative 5, I would be taking the log base 5 of negative 5 in parentheses squared, which would be 25, plus x would be minus 5. Sorry, let me get right here. Minus 5, and then plus 5. So I'd be taking the log base 5 of 25. That's a positive. And by the way, log base 5 of 25 is equal to 2, so that's great. But all that I need to check is that I'm taking the log of a positive number, and I am. All right, let me also check my solution 4 here. So log base 5 of 4 squared would be 16, plus 4 plus 5. And all I'm focusing on is that's a positive number. That's going to be another positive 25. So x equals 4 works as well. So those are both valid solutions. And notice that I'm not kicking out x equals -5. I know it's negative, so it's not that we're just looking at any solution and saying, oh, it's negative, we got to get rid of it. It's when that solution is plugged into the argument, is the argument positive or negative? That's what we're focusing on, okay? So -5 and +4 are both valid solutions. We're keeping them both. All right, let's take a look at number 12. So now it says solve log base 6 of x plus 5 plus log base 6 of x equals 2. And we've got a constant on the right side and then 2 logs on the left. So this is a case where in step 1 we're going to need to condense our logs before writing an exponential form. All right, so condensing, we're going to apply the product rule, log base 6 of x plus 5 times x equals 2. So I condense into 1 log. And then I can rewrite this in exponential form. So 6 raised to the power 2, 6 squared, equals x times x plus 5. I'm just going to rewrite it this way because it looks prettier. And then I can go ahead and rewrite 6 squared as 36. On the right-hand side, let's distribute to get x squared plus 5x. And I see we've got that quadratic x squared. So let's go ahead and set both sides, or sorry, the left side equal to 0. And then just rearranging, I'm going to write the left side as this, x squared plus 5x minus 36 equals our right side 0. Because that doesn't matter. And then usually it's easiest to factor if we can. So x plus 9 times x minus 4 equals 0. Set each factor equal to 0. And we get 2 proposed solutions, x equals -9 or x equals +4. But we need to check both of these. So we'll check both of these. So checking x equals -9, looking at the original equation, I'll split these checks up. So on the left-hand side, we'll have log base 6 of, this guy would be -9 plus 5, which would be -4. And then right there, I know that we fail, right? Log base 6 of -4, that's a domain violation. So x equals -9 is not a valid solution. All right, on the right-hand side, x equals 4. Let's go ahead and check this. So I would have log base 6 of 4 plus 5, which would be +9, plus log base 6 of x, which would be +4, equals 2. 9 is positive, 4 is 4 is positive. Both of my arguments individually are positive, so x equals 4 can stick around as a valid solution. Okay, so if it fails on any of those, you got to kick out the solution, but x equals 4 works. All right, number 13 says solve log base 4 of x plus 2 minus log base 4 of x minus 1 equals 1. So I have a constant on the right-hand side and then 2 logs on the left. Let's go ahead and condense these logs using the quotient rule because of that minus sign. So I'm going to write this as log base 4. Why did that erase? That was weird. Log base 4 of x plus 2 divided by x minus 1. I don't need the parentheses, but I'm just going to write them because they look pretty. Equals 1. And now I'll rewrite this in exponential form. So 4 to the power 1 equals x plus 2 over x minus 1. And then, of course, 4 to the first power is just 4, so I'm just going to erase that exponent. So 4 equals x plus 2 over x minus 1. And then continuing to solve, I could multiply both sides by the denominator, x minus 1. So this gives me 4x minus 4 equals x plus 2. And now we've just got a nice, pretty linear equation. No x squareds or anything like that. So I'm just going to continue adding, subtracting, dividing. So I'm going to move my x, subtract that over on the left. So that gives me 3x. You go bye-bye. And then while I'm at it, I'll add 4 to the right side. So 3x equals 6. And then divide both sides by 3. So we get x equals 2. But before I do our victory lap, let's check and just make sure that solution works. Log base 4 of x plus 2 would be log base 4 of 2 plus 2 minus log base 4 of x minus 1 would be log base 4 of 2 minus 1. So this is log base 4 of 4 minus log base 4 of 1 equals 1. And remember, all we care about, we can check the whole equation if we want, but all that we care about is 4 is positive. The thing we're taking the log of is positive. 1 is positive. The argument, the thing we're taking the log of, is positive. So that means our solution works.